Lecture 4 of Remote Sensing Basics. We've generated light with the sun in most of these cases. Case of passive remote sensing. We've talked about color. We've talked about light going through the atmosphere. And now we're going to talk about interactions with the surface. So, 3 fates of electromagnetic radiation reaching the surface. Sort of by definition, they have to add up to 100, so all incident energy is 100%. And then it's either going to be reflected off objects, absorbed by objects, or transmitted through objects. So that would be the case of like leaves transmit light, water transmits light. Scattering, we should note, is a special case of reflection. And as we'll see, that special case is when light goes off in random directions. So, radiation budget equation, just a little formally presented, is incident radiation is reflected plus absorbed plus transmitted. And so, since we generally deal with these things as percentages, they have to equal 100%. This diagram gives you reflectance, absorption, and transmittance as a function of wavelength from 0.4 micrometers to 1.1 micrometers, and then the y-axis is either reflectance on the left or transmittance on the right. And those two axes are inverted because transmittance starts at 0, no transmittance through the atmosphere or through an object up to some value. So you can see the 3 components of incident radiation change as a function of wavelength. This is for big blue stem grass. So if we look at what we're typically looking at, reflectance, again, the basic pattern of low between 0.4 and 0.5 micrometers. So that's the blue. Higher between 500 and 600 nanometers. Sorry, I switched there. 0.5 and 0.6 micrometers. And then lower again between 0.6 and 0.7 micrometers. And then this increase to higher reflectance in the near infrared. We can see that in the visible between 0.4 and 0.7, this is where light is being predominantly absorbed, and it's being predominantly absorbed to do the work of photosynthesis. And then finally, transmittance. You can see light being transmitted between 500 and 600, sorry, I did it again, 0.5 and 0.6, and to a lesser degree between 0.6 and 0.7 micrometers. And so there's a little bit of transmittance. And then in the near infrared, most of that light is not being absorbed, it's being transmitted through the leaf. So, reflected, absorbed, and transmitted energy dependent on the nature of the surface and the wavelength of the incident energy. So, just to say that on a per wavelength basis, grass absorbs, reflects, and transmits electromagnetic radiation differently than does a fire hydrant. And this is what allows us to tell the difference both in our normal life, looking with our eyes, and for remote sensing. We often use the term reflectance, okay, the percent of light that's reflected from an object. Very often we are talking about hemispherical reflectance, okay, and that's that little rho lambda, that's reflectance as a function of wavelength. So this is a dimensionless ratio of incident energy flux to reflected energy flux. So rho lambda is equal to the energy reflected at a wavelength over energy incident at a wavelength. So if you have 100 units incident, so scaled to a percentage, and 8 units are reflected, then the rho or reflectance is going to be 0.08. And you can see that's calculated for for a wavelength of 0.5 micrometers. And so that's the answer. It's about 0.08 at that red circled point. And this is just showing that generally we're giving this as a percent reflectance rather than a total reflectance. And the reason is that illumination changes. So you might have something on the north facing side of a hill or the south facing side of a hill. Objects in the northern hemisphere on the south facing side of the hill will receive more light, more illumination, and we want to be able to say, independent of the amount of illumination there is, how much, what percent is being reflected. And then we can also look at absorption or absorptance as a function of absorbed energy. So again, at that sort of 0.5 micrometers, that absorption at that wavelength is the energy of absorption at that wavelength over the energy incident at that wavelength. And absorption is given as, can also be written as, 1 minus reflectance plus transmittance. And you can just see we've done the math down there to show the absorptions at 0.5 micrometers. And then finally, hemispherical transmittance is just the ratio of incident energy flux to transmitted energy flux. And so that's energy of transmitted over energy incident. So again, 0.5 micrometers, it looks like about 3 units are transmitted and 100 units are incident. So that gives you a transmittance of 0.03. Reflection occurs when light is directed or redirected as it strikes the surface. Okay, so it's dependent on surface roughness relative to the wavelength, and we'll get into what that means. We have a number of different kinds of reflection we talk about. The first is specular reflection. So with specular reflection, the angle of the incoming radiation is equal to and the opposite of the angle of the outgoing radiation. And this occurs when the surface is smooth. This is the kind of reflection you get from a mirror, for instance. Not a lot of mirrors on the Earth's surface, so when we're looking at the Earth's surface, we're usually seeing this from water or very fine sand that has a smooth top layer. In both cases, you can get specular reflection. We then have near perfect specular reflection, okay? And that's when the angle of incoming radiation is roughly the opposite of the angle of outgoing radiation, because you have a somewhat variable angle of outgoing radiation. So this occurs when the surface is slightly rough relative to the wavelength, okay? So again, very smooth surfaces, in this point, maybe, small rocks, sand that's a little coarser. You can see on the right, you have the angle of incidence and then variable angle of excidence, or angle of outgoing radiation. And the angle of excidence is all sort of clustered around the angle that you would get with a specular reflection. Diffuse or Lambertian reflection is when you have a surface that's rough relative to the wavelength, and then the energy is going to be scattered equally in all directions. So this is when it's equally in each direction, you could think of it as scattering, okay? So you can see there the point that's labeled D, that would be a perfect diffuse reflector or Lambertian surface. In modeling of remote sensing, where we're looking at what we expect to see from a given sensor, we like to have Lambertian surfaces because they make the math easy to do. But really, it doesn't happen very often in the real world. We do get near perfect diffuse reflectors, and you can see that on the bottom there, where there's a dominant angle that would be the angle of excidence, and then you have a variable amount of reflection in a variety of angles. So what kind of reflection is best for remote sensing? As I said, Lambertian makes the math easy. So you'd like to see Lambertian, and the worst is definitely specular, because we get what we refer to as hot spots if we have specular reflection. So all the energy coming back at one or a small range of angles. And when that occurs over water, we call that glint. And these days, you don't see glint very much in remote sensing or remotely sensed images. And the reason is that the people who either fly the airborne data or who set up the orbits for satellites make sure that the satellite is never in a position where you could get glint. So we've talked about reflection, absorption, and transmittance. Now we're going to talk about the patterns of reflection as a function of wavelength for some common land surface types. And the 5 we're interested in is vegetation, soil, water, snow, and clouds. The left axis, or the y-axis here, is percent reflectance. And it's put on a log scale because very wide range, and there are small values we want to pick up, like clear water. If clear water was on the same or on a linear axis, you really wouldn't be able to see the variability in clear water. So it's on a log scale. We're going to start with the reflectance characteristics of green leaves. And you'll be seeing this diagram. Again, wavelength on the x-axis, micrometers. Y-axis, this is percent reflectance. And you can see at the bottom, there's a delineation of the visible, the reflective infrared, and then it's further broken up into blue, green, red, near infrared, and middle infrared. And those will be the portions of the spectrum we're interested in. So 3 mechanisms are responsible for the signatures of vegetation, pigmentation, cellular structure, and moisture content. And each is responsible for separate parts of the spectrum. So leaf pigments show up in the visible. Cellular structure affects the near infrared, and water content affects the middle infrared. So what are the spectral properties of vegetation? What's the effect of leaf pigments? There in the diagram to the left, I'm showing you the absorption features of chlorophyll A and chlorophyll B. And you can see that between them, they absorb between 400 and 500 nanometers and, like 620 and 680 nanometers. And they don't do very much absorption in the green. And so that's the primary pigments we're interested in for our purposes. Of course, on the right, you can see that there are other pigments that display themselves as the photosynthetic materials are withdrawn from leaves, deciduous or broadleaf leaves. During the fall, they change from being green to yellow to brown. I'm sorry, to orange and then brown. And you can see that many different kinds of leaves. And that's all I want to say about that. Returning to this diagram, we're looking at the primary influence on near infrared reflectance, and in this case, it's cell structure. That's the most important factor. And it's the sponginess of the cell structure that's important. So here we have corn, which has sort of an open, spongy mesophyll, the cells inside the leaf, and soybean has less spongy, sort of narrow mesophyll. And so more light is going to be absorbed by the corn, and therefore less light is going to be reflected as shown on the diagram at right. So soybean with those narrow cells, less spongy, is going to reflect more and absorb less. One place that we see this is in the difference between near infrared reflectance for conifers and broadleaf leaves. So broadleaf leaves typically have higher reflectance than do coniferous leaves. And you can see that very easily if you're looking at an image that has near infrared information. You can see the distinction between those two kinds of crowns very easily. Back to this diagram, we're now concerned with water content, and that's the factor that's primarily responsible for variation in the middle infrared. And you can see that I've identified 3 water absorption features in the mid-infrared. These 3 features are sensitive to either water in the atmosphere or water within the leaf. So the lines in this diagram and the box colors on the right are key to each other as you go from low moisture content, so a very dry leaf, to high moisture content, very wet leaf. These water absorption features lower the reflectance of the leaf. Okay, so low moisture content, high reflectance, high moisture content, low reflectance, and you can see the increase in those water absorption features. I'm not sure why that's there. Oh, show you the distinction between the green characteristic of crowns and the visible, and then this is a what's known as a color infrared image, and we will talk about these more later. Okay, now we're going to talk about soils. So there are a lot of factors can modify the spectral qualities of soils. And the primary ones are the amount of organic matter, the texture, the presence of iron oxides, moisture content, again, and surface roughness. And that diagram at left shows you vegetation spectra, which should be getting familiar to you, and then the contrasting spectra for soil. And you can see there's this classic pattern of low reflectance in the visible, starting at, in this case, 0.5 micrometers, increasing through the visible and the near infrared, and then sort of a more or less constant reflectance in the mid-infrared. So, water absorption, well, I should say increased organic matter. Organic matter, you should be probably familiar with. It's dark. The more organic material there is in the soil, the darker it will appear. So as you go from 0.8 to 20% organic matter in the soil, you see two things, one of which is the overall reflectance goes down. But the other thing is those water absorption features become deeper. And that's predominantly because soils with higher organic matter in them, organic matter tends to bind or contain more water, and therefore you get that same water absorption feature that you would get in leaves, for instance. Increased iron oxides on the left, those give you decreased reflectance, so those soils become darker. A coarser texture is also associated with decreased reflectance, and so as you go from a finer silt or clay, those have higher reflectance. Sand has a lower reflectance, and then finally muck has the lowest reflectance. Muck is a soil that has a lot of organic matter, so muck is really that low reflectance is more due to the organic matter that's in the soil. Increased moisture content, decreased reflectance, and more prominent water absorption features in the mid-infrared. And finally, increased roughness. And here we're talking about the surface of the soil, whether it's been, whether it's relatively flat or whether, for instance, it's been plowed. So plowed condition, that's crust broken. A smooth surface would be crusted, and when you break up the crust, you have more opportunities for light to interact with the soil surface more than once. So if you have a smooth soil, light's going to come in, be reflected once. You have the possibility with when you break up the crust, you get that roughness, and the light may interact with more than one surface, therefore lower reflectance. And here's an example of soil moisture, giving you an idea of processes that are going on in the soil. This is a color infrared image. So the red areas are vegetation. And so we've got a field, it's got an irrigation ditch going through it. And then around the irrigation disc and another area to the lower right, these are areas that have more surface moisture and are becoming darker. Water. Water has a complex spectral responses because other materials get mixed into it. So you've got what we would call multiple scattering going on. You've got light coming in, it's interacting with the water, and then it might interact with something dissolved in the water, and then it might interact with water again. So you've got sort of a complex path in the water before it's maybe reflected out to your eyes or a sensor. As water depth increases, red light is most quickly absorbed, green light more slowly, and blue light is most slowly absorbed. And so on the left, you go from, there's an area where you're going from low depth, and as you go to the right, you're getting to deeper depths. You can actually use the spectral information there to infer the depth of water based on how dominant the blue light is. On the bottom, we're looking at a situation where two streams are coming together, and you can see one of them is turbid, that is, it has soil mixed in it, and one is relatively clear. On the right, you can see how the spectral qualities of the combination of water and soil changes the spectral qualities. And whereas water is low reflectance and soil is high reflectance, when you mix them together, you get this non-linear effect due to the multiple scattering. Another type of multiple scattering that can go on in water is when there's chlorophyll. Okay, so when you've increased algae or phytoplankton in the water column, it increases the relative reflectance in the green wavelengths and in the infrared. You still get some absorption in the blue and the and red, but you can see again it's not a linear relationship between a simple mixing of the spectra for water and chlorophyll. Clouds and snow. Clouds and snow, you may have seen this, they are both white. They are both white in the visible. Clouds have high reflectance in the mid-infrared as well. And this is true because clouds are non-selective scatterers. So it's non-selective. They're always going to have high reflectance. Snow, on the other hand, has low reflectance in the mid-infrared. And you can see there in these images on the left, you've got the same area. You have sort of an undifferentiated white area when we're looking in the visible. When we're looking at the mid-infrared, though, you can see that some of those areas have turned dark. Those are the snow areas, and you still have some bright areas, and those are the clouds. And so mid-infrared is used to map snowy areas from space. So we have different kinds of reflection, specular and diffuse. We have reflectance, which along with absorptance and transmittance gives you 100%. You've accounted for all the light incident on an object. And then reflectance spectra vary for different types of land surface materials, and we've reviewed those.